Alright, time for draftphysics.com, debatephysics.com also, video presentation. So this will be a response video. So that's what I will qualify it as in the title somewhere. And do something just so you know the difference between the videos, just to enhance audience participation, something. Anyway, Leksa has made a video and regarding trying to argue that Leibniz was in some way correct in stating that lifting 4 pounds 1 foot is the same as lifting 1 pound 4 feet. As I pointed out, it's all about time. So you could lift the 1 pound really, really slowly, okay, and make it 10 times more energy to lift the 1 pound than it takes to lift the 4 pounds, the 1 foot. And vice versa. You want to make the 4 pounds more work? Well, then just lift it really, really slowly. Again, I think he's just verifying my argument that it's all about the time, and you can figure that out. So he's, I could play the video, but maybe I can explain it quicker than he can in animating it. Alright, so you start off with 4 pounds at this level. You're going to end up with 4 pounds, okay, 4 little balls 1 foot higher, let's call it. And you're going to use the energy of 1 ball 4 feet, okay. So what you're basically arguing is that you could take the 1 ball, sooner or later it's going to go up there, and expend the energy to lift it the 4 feet. And now I can use that energy to lift these other 3 1 foot and leave this one 1 foot. And so I'm going to use these 3 feet of energy to lift these 3 1 foot, blah, 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 and somehow there. That's an equality. The trick is you can't do it. Okay, it's a perpetual motion machine kind of idea. You can't make one in reality. So you can't come up with a device that will actually do this this inverse lever thing where I drop this and this rises through the dropping distance, without the extra of the motion first and then hitting the lever. So it's just like kind of putting something on a scale that's already got a weight on it. I got a 1 pound over here and I'm going to put a 1 pound over here. It's not going to lift it up. And if I drop it and it hits, well, then it's going to move the lever, so I'm going to lose my distance. So there's 2 things you got to consider. You got to consider collecting the energy, that is collecting the velocity, and then you have the distance it takes to transfer it. So transferring energy uses distance, and that's the catch. Or it uses efficiency, in the sense that the spring you put it into will be so inefficient you won't get the same energy back, and so it just won't work. But yeah, in theory you can do more work. So I guess let's just finish this up. So you would drop the first thing 3 units of distance to raise one thing 1 unit of distance. No, that isn't how we said it. Wouldn't work that way. It's funny that he drew it that way. Alright, well, let me just start here and then we'll let him say it.
And then we can let it drop back down 3 units of distance. And we can store the energy, for example, into a spring, and use that energy to lift this object up 3 units of distance.
Okay, so he did,
and again let it fall back.
Right, I just did the shortcut where you just drop it the 1 for 1, 1 for 1, 1 for 1, and he's doing it 1 to 3, 3 to 3, and then 2 to 2, and then 1 to 1 in terms of lifting distance, and then letting it fall again. So he's letting that new object fall and lifting, and then fall, and then lifting. So again, but it just doesn't, like I said, you can't build it. So obviously you can say it's the same, but in the physical reality, if you can't build it, it's kind of demonstrating it's not the same. Yeah.
down.
So let
2
me finish
units of
it.
distance. Store the energy. Use that energy to lift this object up here. Let it fall back down. 1 unit of distance. Store the energy again and use it to lift this object up.
Right. So how do you store the energy? Right. So there's no Newton's cradle version of this where I could just take a piece of steel or something and let something hit it, and I get something else bounce back up. This doesn't happen. So what I have to do is use a lever or something else to translate the motion. And so obviously I'm going to lose the motion in the translation process, in the transfer process. So the transfer process requires a unit of time. And that unit of time is what you can't afford to give away, especially in the sense that you're losing distance, which you need not to lose any. You can't lose any of the distance by applying it over more time. So I guess there's analogies for this, right? It's always work. Every time something's sitting on a surface, it's doing work. So I could lift an iron and put it on an ironing board. And I could leave it on the ironing board for a millisecond and do almost no work. Or I could leave it there for 3 minutes and it's doing lots of work. So, weight, putting pressure on. So clearly there's no surprise that you can convert it into more work. So then I'll draw from here an example that's simpler than his example, and just to point out that that's it's always going to come down to time, and that you can't do it without using more time. Okay, so you can't do it in the same amount of time. All right, is this off? So far off, actually. It's a little better. All right, so the problem is that you first have to collect the energy by falling. That's the only way you can have a velocity, is you have to fall in the gravity free fall. You don't have any velocity if you're not free falling. And then there's going to be the transfer problem, is that if you used a lever, you clearly have to transfer with a whole bunch of motion to get the motion of the other object up. So you're using 2 units of distance, and so this won't work. And so the example I thought of was if you had a step that went down, okay, and this was your weight, okay, and you're going to use it to drive something into the ground. Okay, now I have to do that. All right, and then you use the counter example, like of just a pedestal. All right, so you're going to use the same energy. I'm going to drop something, so it's 4 units of height. I'm going to drop it, but I'm going to drop it in these 2 ways. So if I let it fall, all I'm going to get is 9.8 here in velocity, and then another 9.8 in this part here. So I'm going to have the 19.6 when I'm done velocity. So I only got 2 units of gravity. 2 seconds is what this will take. Now if I do it this way, it'll take 4 seconds. So if I let it fall, and then fall, and then fall, and then fall, it has to have a little platform here. It's going to take 4 seconds. So I'm going to get 4 seconds worth of free fall. It's going to, this is a unit of free fall, this is a unit of free fall, this unit of free fall, this unit of free fall. So I got 4 units of 9.8 theoretically, of 9.8 plus a mass and a velocity, and it's clearly more energy. So I would clearly argue that this will impose more energy. So it's an experiment I intend to try to do. It just comes down to taking a mass, a 1 mass, dropping it from 4 times the distance, and then dropping it 4 times from 1 unit of distance, and seeing how much compression it can cause in clay or something else. So the fact is you can derive more work out of it, but that work can't be lifting, because you can't beat the efficiency of velocity in terms of lifting something. You can't lift it slowly and still be just as efficient. And so until you can convert the slow movement into a fast movement, that's where the catch always is. That's where the Newton cradle fails. That's what the real controversy is really about, is the fact that it's hard to take the total energy in one thing, a small thing, and put it into a big thing, or vice versa. That's the complication. Alright, so that's probably enough. So there's no, you've established no equality in the sense that you can't turn this into real work. So if you could really build this machine, then you'd have an argument. But you can't build it, you can't make it happen. So therefore it's not really an argument that the same are the same energy. And it clearly illustrates my point that if you did it this way, you're dropping it in 4 units of time. So you really are just slowing down how fast it free falls, and by slowing it down, gaining a little bit more weight out of it. And yeah, that works both ways. It's more work to lift it slow. It's more work you can gain by dropping it slow. So every time you use a weight, whenever they use a weight on a pulley and they let the weight fall down, they're slowing down how fast the object falls. And by doing that, they're gaining more energy from its mass falling, because they've slowed down how long they've taken the same thing that's happening, falling, and they've made it take longer and extracted more energy. So if you just let it free fall, or if you pushed it fast through the gravity, obviously you get even less extra energy. You wouldn't be able to move the car as fast with this falling energy, free falling. So at the free fall speed, you wouldn't gain enough energy to roll a car, where you will gain enough if you basically let it fall in little increments. And that's essentially what is happening when you tie the string and let it fall at a slower rate to move the car. You're gaining more energy because you're gaining more gravitational weight. The object weighs its weight longer. It's yeah, it's weighing its weight longer. I don't know how else to say it. You're collecting the weight for a longer period of time. You're in the force a longer period of time, collecting the force's radiation. And so it's just like the photon argument. That's why they share the inverse square law. It's because it's just like photons. The more you get hit by, the more you collect, the more energy you're getting. And so any mechanism that slows down, that it creates more exposure to a stream of photons, will also get you more energy. Alright. Don't know how else to say it. What else needs to be added? So, but there's no equivalency in terms of you can't make your one mass 4 times the height actually lift the 4 pounds 1 foot. So you can't actually make it do that. So, and I can't actually make the 4 pounds lift the 1 pound. Plus extra, I can get even more out of it. Alright, so that I guess would be a simple proof, is how far can I throw the 1 pound with the 4 pounds dropping 1 foot. And the fact is I can throw it higher than 4 units of distance. Alright, so till the next time and such. I think that's enough. And see what his counter argument is. Okay. So the real obligation is to find some mechanism that demonstrates that you can collect, you can convert, you can transfer the extra energy into real lifting. And that's the catch. There's, the springs won't do it and levers won't do it, so you have to find some other mechanism that doesn't require you to lose the energy to collect the energy. Alright, so your example takes for twice the time. So if it was 1 second, blah blah blah, if it was 2 seconds to drop the 4 distance in free fall, by stopping it from free falling the full distance, you will increase the time that it's in free fall. So it will be twice the time that it's going to take it to go through the cycles that you're requiring. Just as it would take 4 seconds for it to go down the staircase, even if I made the motion across the stair instantaneous, it's still 4 seconds, 4 units of 9.8 at the rate of acceleration from 0. So you're stopping it, letting it go, stopping it, letting it go, stopping it, letting it go. It's going to be 4 units of time. Same thing as what you're doing. And it's the argument I'm making is that it's a time-dependent force. So obviously you're not disputing time dependency. I just throw in that the Chardonnay clay experiments, I guess it was a German guy who invented those, and he actually believed in perpetual motion. So both Leibniz and Newton said perpetual motion wasn't possible, and they just accused each other of defending a theory where perpetual motion was made possible. But that guy believed that it was, and actually, you know, it was kind of tough traveling places back then. He would travel very long distances to go research somebody who claimed to have a perpetual motion machine. So he thought it really was realistic. And yeah, it's reasonable to have some, to not be able to follow exactly the rules of the transfers, because they do seem inconsistent. It seems like you should be able to store the energy horizontally, and then just turn it and apply it vertically. But you can't. There's always a rule or some kind of mechanism gets in the way. So the physics just doesn't allow you to take advantage of dropping things slower to make something else move faster. You can only apply the energy over a longer period and gain more from it, but you can never apply it over a shorter period of time. You can't collect the more over a longer period of time and store it. The storage devices don't allow you to store it and then release it, apparently. And I guess some of that we might be seeing with springs, and the fact that they don't seem to be capable of producing the amount of energy. They seem to lose a lot more energy than maybe we all thought. But we'll see in terms of translating if you change the speed. But we'll have to do more experiments before I'll draw a conclusion on that subject. So anyway, alright, so it was probably enough of a statement and such. Thank you for the argument. Bottom line, if it were true, then you could build one, but you can't build one, therefore it's not true.